Welcome to AI Paper Slop, the YouTube series, where we summarize the latest AI and tech papers for you. Today we are looking at a paper called EasyOPD, an easy-to-use on-policy distillation framework for large language models. This is authored by researchers from the University of Science and Technology of China, Tencent, the Shanghai Innovation Institute, and the National University of Singapore. And look, I want to give you the core insights straight away. On-policy distillation, or OPD, is vastly superior to offline distillation for preventing what we call training inference mismatch.
Right. It's night and day in terms of performance.
Yeah, but the problem is it has become a total software engineering nightmare for AI researchers. Every new OPD method requires entirely custom implementations for rollout generation, for teacher inference, and token alignment. It's just a mess. So EasyOPD solves this by introducing a unified three-layer framework built on top of the verl distributed execution substrate.
Exactly. And by isolating the method-specific supervision logic using what they call thin hooks, EasyOPD allows ML engineers to just swap entirely different distillation paradigms like Cross-Tokenizer alignment or self-distillation or stepwise supervision just by changing a single YAML configuration file.
Which is, it's a massive quality of life upgrade for technical practitioners. If you're tired of writing custom hyperfragmented training loops, this is for you.
Oh, totally. To really appreciate the scale of this, this upgrade, we kind of have to look at the baseline. Like, what are engineers currently wrestling with? If you're building LLMs today, your stack probably involves frameworks like TRL for those trainer-centric APIs.
Right.
Or maybe you're using Slime for scalable rollouts or KD Flow for your distillation stack. And look, those frameworks handle specific pieces of the puzzle beautifully. They really do. But none of them, absolutely none of them, provide a single unified interface for highly heterogeneous OPD methods across multiple distributed nodes. EasyOPD bridges that exact gap. It gives you a single entry point for wildly different supervision interfaces, so you don't have to rewrite your entire distributed training loop from scratch every time you want to try a new idea.
Which sounds like absolute magic for anyone who's been dealing with these hyper-fragmented code bases. But before we get to this YAML swapping utopia, I want to make sure we understand the baseline pain here.
Yeah, let's dig into it.
What are the fundamental mechanics of why offline knowledge distillation is failing researchers, and why is the pivot to OPD so technically painful?
Well, the fatal flaw of conventional offline knowledge distillation is really the static nature of the data.
Okay.
Traditionally, whether you're doing like sequence-level distillation or token-level KD, you train a smaller student model to imitate a larger teacher model using fixed offline text datasets.
Right, so the textbook approach.
Exactly. The student learns to match the teacher's next token probability distributions based on a static set of prefixes. So the teacher basically evaluated a perfectly written text, and the student just learns to predict the next word of that perfect text.
Wait, so if the student model hallucinates even one word during its own generation, like out in the real world, does it essentially fall off the map of its offline training data?
Yes, that is the exact point of failure.
Because now the context it's looking at isn't the perfect offline text anymore. It's a text containing its own mistake, right?
Precisely. During autoregressive inference, the student model conditions on its own previous predictions. So if it makes a tiny deviation, say it predicts the word therefore instead of however, it suddenly finds itself in a context space that was poorly covered or not covered at all by the offline training data.
Oh, wow.
And because the process is autoregressive, it feeds that slightly corrupted context back into itself for the next token.
The compounding error.
Exactly. The errors just snowball across the decoding steps. We call this a training inference distribution mismatch. The offline prefix distribution simply doesn't track the current student's actual rollout distribution. So the teacher's probability calculations from the offline data, totally useless now because the context is essentially alien.
It's like trying to learn to drive by exclusively reading a static textbook.
That's a great analogy, actually.
Right. Like, in theory, you know how to steer, you know how to brake, but only based on perfect dry road conditions. But the second you hit an unexpected patch of ice in the real world, you drift slightly off the textbook's path. And because you've never practiced recovering from that specific skid, you just overcorrect and end up in a ditch. The compounding error ruins the whole trajectory.
Yeah, and that is exactly where on-policy distillation comes in as the fix. The defining property of OPD is that supervision is collected on states induced by the current student. So the loop works like this. The student generates rollouts, meaning it actively predicts a full sequence. Then a teacher model, or maybe a reward evaluator, looks at those specific self-generated rollouts and supervises them.
Ah, I see.
So the student updates its policy based on its own actual mistakes in real time.
Yeah.
Going back to your analogy, you finally have a driving instructor in the passenger seat correcting your actual real-time driving rather than just, grading a written test you took in a classroom.
Which sounds brilliant algorithmically. Like, of course you'd want to train that way. But then you hit the software reality, which is the system nightmare. Doing OPD right now is like having to physically build the car, manufacture the passenger seat, and then genetically engineer that driving instructor from scratch for every single driving lesson.
It really is. The complexity scales absurdly fast because while the algorithmic paradigm is common, the system interfaces are just wildly divergent.
Oh, so?
Just think about what a distributed OPD pipeline actually has to do under the hood. It has to coordinate rollout generation across multiple GPUs. It has to manage teacher inference, which might require completely different memory constraints than the student. It has to construct rewards, handle distributed data flow, and run optimization algorithms like standard reinforcement learning or PPO.
That's a lot of moving parts.
And it gets worse. If you're doing Cross-Tokenizer OPD, you have to mathematically align tokenizations between the teacher and student before you can even construct a compatible loss signal.
Oh, because they literally don't speak the same vocabulary.
Exactly. Or let's say you switch to rubric-based OPD. Suddenly you're converting textual judgments from an LLM as a judge into numerical rewards. Switch to stepwise OPD, and you're tracking multi-turn agentic supervision across a timeline. Building this massive distributed pipeline from scratch for every single one of these experiments just absolutely kills iteration speed.
So how does EasyOPD actually decouple this? I mean, how do they separate the specific supervision logic of the experiment from that heavy system engineering required to keep the GPUs humming?
Well, they utilize a really elegant three-layer architecture. Layer 1 is the user layer. This is designed for minimal user-side invocation.
Okay.
You interface with it via Python or just the command line. And your hyperparameters, your model paths, your data sets, they're all managed purely by YAML configs. You don't even touch the training loop.
Love that. Keep it simple.
Right. Then layer 2 is the EasyOPD layer. This encapsulates the method local OPD logic. It contains a unified method library encompassing things like GKSD, SimCT, SOD, and a central method registry.
Got it. And then layer 3 is the verl execution substrate. This is the shared distributed backend doing the actual heavy lifting, right? The PPO or distillation trainer, the scalable rollout engine, the distributed workers managing pipeline parallelism. But I want to push back on this reliance on an existing framework for a second.
Oh, sure. Go ahead.
If they're trying to build the ultimate unified OPD framework, doesn't tying EasyOPD to an existing backend like verl risk inheriting all of verl's limitations? Why not just build a completely unified, brand new framework from the ground up to ensure everything is perfectly optimized for distillation?
I get that instinct, but building a distributed training system from scratch introduces infinitely more bugs than leveraging a mature substrate.
Fair point.
It really comes down to a fundamental balance of expressiveness versus maintainability. The system-heavy components of OPD, like worker orchestration across multiple nodes, handling tensor parallel and pipeline parallel memory constraints, large-scale optimization, these are incredibly complex to build and maintain. verl already masters these components.
So rebuilding that would just be reinventing the wheel.
Completely redundant, and frankly, a waste of engineering hours. What EasyOPD contributes is a highly expressive dispatch layer on top. By using what they call thin hooks, they keep the method logic entirely local and isolated, while relying on verl as a hyperstable shared engine block.
Okay, so let's dig into the mechanics of these thin dispatch hooks, because that seems to be the core innovation. How do they actually route the data flow in practice without getting tangled up in that backend? If we go back to our car analogy, where verl is the chassis and the engine of the car, what exactly is a hook?
Think of a hook as essentially a universal plug-and-play dashboard. It exposes a stable interaction point in the training pipeline where you can inject custom logic without altering the underlying engine at all.
Yep.
EasyOPD defines a small, highly specific set of these boundaries. For example, you have loss hooks. These intercept the logits to compute token or distribution level supervision.
Right.
You have rollout hooks, which attach trajectory metadata to the generation process so you can track, what happened at step 3 versus step 10.
Very useful for agents.
Exactly. Then there are reward hooks to process judge or rubric feedback, alignment hooks for mapping token or span level discrepancies between different models. And finally, teacher sidecar hooks.
Teacher sidecar hooks, what do those do?
They're responsible for routing teacher-side signals, like hidden states or logits, without disrupting the student's active memory allocation.
Ah, okay. So the registry just activates the specific hooks a method needs. Like if I'm running a standard logit-based objective, I just need a loss hook.
Exactly.
But if I'm tracking stepwise multi-turn data, the registry activates the rollout metadata hook as well, leaving the rest of the pipeline completely untouched. The verl backend doesn't even need to know what kind of distillation is happening. It just knows where to pass the tensors.
You nailed it. It fundamentally changes OPD integration from a massive framework-wide surgery into a simple method local extension. You change the YAML config, the registry flips the necessary hooks on the dashboard, and verl just keeps chugging along underneath.
It makes a lot of sense in theory, but I really want to see how this universal dashboard handles mismatched parts. Because a framework's architecture might sound great on paper, but it only really matters if it can handle wildly divergent heterogeneous OPD methods used in cutting-edge research without completely breaking.
Very true.
And the paper actually stress tests EasyOPD across 3 extreme settings. Let's start with stress test 1, Cross-Tokenizer OPD.
Right. So this is a notoriously difficult setting that usually just breaks standard OPD pipelines right out of the gate.
Why is that?
Well, standard on-policy distillation relies on directly comparing the next token probability distributions of the teacher and the student. But what happens when the models use entirely different tokenizers?
Oh, the math just doesn't line up.
Exactly. In this test, they distilled a Qwen 2.57b model, which has a vocabulary size of about 151,000, into a Phi 4 mini student, which has a vocabulary size of over 200,000.
So the token spaces are completely misaligned. I mean, a token ID of 12 in Qwen's vocabulary might represent the word apple, but in Phi 4's vocabulary, a token ID of 12 might represent the word galaxy.
Precisely.
You can't just run a mathematical divergence calculation on those logits because the dimensions and the actual meanings don't match. How does EasyOPD map these without breaking the pipeline?
It handles it purely via the alignment and loss hooks. Instead of writing a massive custom training loop just to align the models, the alignment hook intercepts the logits right before the loss is calculated. They actually tested 4 different cross-tokenizer methods on this exact same setup to prove the modularity. They tested SimCT, ULD, ALM, and DSKD.
Okay, take SimCT, for example. How does that work in the hook?
Instead of forcing a direct one-to-one token match, SimCT leverages the alignment hook to map both the teacher and student distributions into a shared semantic anchor space. It often uses like vocabulary overlap or projection matrices to do this.
That look clever.
Right. So the hook performs this translation, computes the compatible loss, and then sends the gradients back down to the student. They warm started this student on a 10K math and code corpus and gave all 4 methods the exact same optimization budget just to see what would happen.
And how did it perform?
Really well. All 4 methods improved the unweighted average over the base student model, but SimCT was the absolute standout. By gracefully mapping those disparate vocabularies, it achieved an average score of 53.5 across the benchmarks.
Wow.
Yeah, that's a solid 3.3-point bump over the base model, and it outright won the Math 500 benchmark. ALM led on MBPP and Live Codebench V6, while DSKD took GSM 8K.
But the critical takeaway for a practitioner isn't just who won the benchmark, right? It's that all these distinct cross-tokenizer objectives ran through EasyOPD's interfaces under a perfectly matched setup. They retained their distinct performance profiles, and nobody had to write a custom training loop.
Exactly. The iteration speed is the real winner there.
It's fascinating that the framework handles separate models with entirely different vocabularies so smoothly. But what happens when the student and the teacher are the exact same model? Does the architecture break down when it has to self-evaluate? That brings us to stress test 2, on-policy self-distillation, or OPSD.
Yeah, this is a great test. For this one, they used Qwen 3.8b as both the student generating the response and the self-teacher re-evaluating it with additional feedback.
Wait, if it's evaluating itself, how do you prevent the model from just blindly agreeing with itself? Like, yes, I am brilliant, A+.
Yeah, you have to break the symmetry. To prevent that, the teacher version of the model is typically updated using an exponential moving average, or EMA.
EMA, okay.
Essentially, the teacher is a slow-moving average of the student's weights over time. It creates a slightly more stable, mature version of the student to act as the evaluator.
Okay, but how do the hooks manage that? Because running two slightly different versions of an 8 billion parameter model
Yeah.
simultaneously sounds like an absolute memory routing nightmare.
It really exercises the framework's ability to seamlessly instantiate teacher and student policies from the same model under different conditioning contexts. They utilize that teacher sidecar hook we talked about earlier.
The sidecar.
Right. The hook manages the routing of the EMA teacher's logits and hidden states, ensuring that the self-evaluation signal is cleanly separated from the student's active generation memory. They actually compared SDPO, a self-distillation method, against standard reinforcement learning using GRPO, and they ran 1 hour and 5 hour wall clock budgets.
And the performance differences were pretty stark depending on the task, right?
Very much so. SDPO absolutely dominated on the chemistry and biology benchmarks from Sinoeval. At just the 1 hour budget, SDPO showed a massive plus 19.2 point gain over the baseline on chemistry.
Almost 20 points in an hour.
Yeah. GRPO, on the other hand, was stronger on mathematical reasoning and GSM-8K and on the 5 hour tool use evaluation. So the performance is highly task-dependent. But from a systems engineering perspective, the framework handled the self-teacher interfaces flawlessly. It dynamically managed the EMA weights without choking the verl backend.
Incredible. So we've covered mismatched tokenizers and self-teaching models. What about when we introduce time and sequence? Like multi-turn agents, for instance. That brings us to stress test 3. And here's where the mechanisms get deeply interesting to me. Stepwise OPD.
Oh yeah, this is for long horizon agents and tool use scenarios.
Right, because in these multi-turn trajectories, a mistake early on can completely poison the rest of the steps.
Exactly. Think about, a multi-step math problem or a coding agent querying a database. If your agent hallucinates a database query on step 2 and retrieves just total garbage data, applying uniform teacher supervision to steps 3 through 10 is totally counterproductive.
Because the states are already corrupted. The agent is operating in a hallucinated reality at that point.
Right. Standard response level OPD applies a single reward or supervision signal uniformly across the whole trajectory. But stepwise methods, like SOD, which stands for stepwise divergence, they reweight the distillation loss dynamically based on step-level student-teacher divergence.
Okay, but how do the hooks handle tracking that timeline? Because you have to know exactly where the divergence happened in order to reweight the loss.
They used a Qwen3 1.7b student and a GRPO-optimized 4b teacher for this setup. EasyOPD deployed SOD using those rollout metadata hooks.
Okay, I see where this is going.
So as the student generates a multi-term trajectory, the rollout hook attaches metadata to every single step, tracking the state and the action taken. When the teacher evaluates the trajectory, the loss hook looks at that metadata and calculates the divergence at each specific step.
So if step 2 diverges wildly, the hook knows it.
Exactly. The hook downweights the supervision signal for the subsequent corrupted steps. This prevents the student from learning bad behaviors from states that are already ruined.
And the results prove the mechanism works, right? Looking at AIM 2024, AIM 2025s, and Live Code Bench, SOD scored an unweighted average of 39.95 compared to standard response level OPD's 34.81. That is a plus 5.1 jump just by dynamically reweighting the step-level divergence. And again, all of this complex state tracking logic was handled gracefully through the metadata hook without ever disrupting the verl substrate.
Which is the whole point. It takes the focus entirely away from distributed systems debugging and puts it back on algorithmic design where it actually belongs.
I really want to highlight the sheer convenience here for you, the listener. Think about what we just unpacked. Going from a cross-tokenizer alignment problem, literally mathematically projecting mismatched vocabularies into a shared space, to tracking multi-turn agent steps and dynamically reweighting loss across a timeline. Those require entirely different supervision spaces.
Completely different.
In the past, testing those two ideas meant writing two entirely separate code bases and spending weeks just debugging out-of-memory errors. But in EasyOPD, the ML engineer literally just ran the same execution script and swapped a YAML config from, sync.yaml to sod.yaml. It was like changing the underlying physics engine of a video game just by editing a single text file.
It truly democratizes access to complex distillation. And for those looking to implement this in their own work, the practical implications are huge. The project is fully open source under the Apache 2.0 license.
Oh, awesome.
Yeah, they've provided an installable package, runnable YAML configurations for all these stress tests we just talked about, and some really brilliantly documented diagnostics.
Let's actually talk about those diagnostics for a second, because when a training run fails in machine learning, Looking at the final loss scalar isn't enough. You just see a number go up instead of down, and you have absolutely no idea why.
Right, it's so frustrating. But because EasyOPD isolates the method local logic within the hooks, it can expose supervision-specific diagnostics that standard frameworks just completely obscure.
Give me an example.
Well, for cross-tokenizer methods, the alignment hook reports the overlap vocabulary size and the valid span ratio in real time. So if your loss is spiking, you can look at the diagnostics and see, my vocabulary overlap calculation is too small. The models just aren't speaking the same language.
Oh, that is so useful.
Right. And for stepwise methods, the rollout hook tracks the mean step-level weight. You can actually see why the signal is failing mathematically rather than just knowing that it failed.
It fundamentally changes OPD integration from a massive framework-wide modification into a simple localized extension, which actually leads me to a final thought for you to mull over as we wrap up this deep dive into the source material.
Love a good hypothetical.
Now that the friction of swapping distillation methods has been completely removed, literally reduced to just editing a few lines in a YAML file, could we see the emergence of dynamic curriculum distillation?
Oh, wow. That is a fascinating application of the architecture.
Right. Just imagine a training run that starts with standard cross-tokenizer alignment to get the student up to speed on the teacher's basic vocabulary. Then the system automatically detects a performance plateau. Because the hooks are so thin and modular, the system hot swaps the YAML config to stepwise trajectory weighting mid-training. It just injects complex multi-turn reasoning supervision without ever stopping the distributed execution loop.
That's brilliant.
The car doesn't just have a driving instructor in it. The car is dynamically reassembling its own engine and swapping its tires while speeding down the highway, all depending on the weather conditions.
I mean, if the dispatch hooks can be updated at runtime and the verl backend remains stable, dynamic curriculum distillation isn't just possible, it is the absolute logical next step for this kind of modular architecture.
Definitely something to think about for your next distributed training run. Thank you for tuning in to AI Paper Slop, and we'll catch you on the next deep dive into the source material.